So our last presenter this morning is Shalini Kurinchi-Vendhan, who's joining us from Caltech, where she'll be a junior this coming fall. Shalini's been working with Xiaolong this summer, and she'll tell us today about her project, Collapse of Fuzzy Dark Matter, an exploration with simulations. Go ahead whenever you're ready.
Sure, thank you for the introduction, but I'll go ahead and get started because I'm sure a lot of people are wondering what fuzzy dark matter is and why it's interesting. So dark matter is one of these really compelling questions in cosmology, and it's one that we can try to explore with modern simulations. And here's an animation of one of these simulations, which shows the evolution of the dark matter distribution from after the Big Bang up till the present day. And in these simulations, dark matter builds the backbone for the formation of galaxies, which are expected to form at the centers of these dark matter overdensities. And these so-called gravitational halos collapsed and pulled surrounding gas into their cores, which eventually cooled and condensed into the first galaxies. And so we're interested in understanding this process of collapse. The most prevalent model is called the cold dark matter model, which is made of these cold, massive, and slow-moving particles. But physicists have also hypothesized the existence of fuzzy dark matter, which is made of these ultralight particles that behave in a quantum fashion, and this gives it wave-like properties on galactic scales. And if you run simulations using each of these different models, like we saw before, you'll get pretty similar results. At first glance, these dark matter distributions might look identical, but in terms of their filamentary and clumping structure. But if you look closely, you'll notice that the cold dark matter case has a lot more overdensities than the fuzzy dark matter case. And in fact, it has too many. And this is indicative of some small scale problems with the cold dark matter model. For example, on the left is a Milky Way-like simulation using cold dark matter that has hundreds to thousands of surrounding satellites. Meanwhile, our own Milky Way has around 50 known satellites. And so there's this discrepancy between observations and simulations in terms of the number of purely dark halos and which of those actually lead to galaxy formation. Meanwhile, fuzzy dark matter might be able to address some of these small scale problems. You can see that it leads to less overdensities in the distribution. And this is because it's additionally affected by something called quantum pressure, which suppresses overdensity growth. And it's able to do this because in our classic understanding of spherical collapse, gravity pulls in dark matter to a single point. But in fuzzy dark matter, quantum pressure acts like a repelling force, and this results in a minimum requirement for collapse to even occur. And this can constrain the amount of satellite galaxies in simulations. But modeling the effect of quantum pressure is still an area of active research. Current studies are often constrained to simple one-dimensional problems in simulations. And in this way, a more comprehensive analysis of how quantum pressure affects the collapse of dark matter halos and thus small-scale structure formation is needed. And so we want to know how exactly do dark matter halos collapse in the fuzzy dark matter model. And to investigate this, we'll be using 3D numerical simulations to model the evolution of fuzzy dark matter halos over time. And then we're going to make use of a semi-analytic treatment to predict how likely it is for these overdensities to develop into halos. The goal is to simulate the collapse of a single dark matter halo over time in both the cold and fuzzy dark matter cases. And the very first step to do this is to set up appropriate initial conditions for both sets of simulations. And unlike in previous studies, we're focusing on a single halo so that we can use a huge number of particles in a small volume to get high enough resolutions in our results. And in terms of constructing the initial halo itself, we'll start with the smooth density field of particles. So here is the overdensity of the halo with respect to the distance from its center. And then we're going to perturb it so that it has a high central overdensity. And this initial amplitude is what sets the initial growth of the overdensity, is what causes the halo to collapse. And then we can also control the size of the halo by setting its mass, and this in turn will affect its radius. So we can get the distribution of the particle positions from their density field. And then we can also use a continuity equation which relates the density to the velocity to get the radial speeds of the particles. And here it's important to note that inside of the halo radius, the particles should be moving toward the center. In the end, I was able to run 4 sets of simulations for cold and fuzzy each, and also specifically for halos with 2 different masses and also with both low and high initial overdensity amplitudes. In the cold dark matter case, we're using the gadget code, which is a gravitational n-body simulation. And then we'll use the same exact initial conditions to run our fuzzy dark matter halos, where we're using a spectral code, which my mentor previously developed. And unlike the n-body code, it numerically solves the Schrodinger-Poisson equation for the wave function that describes the fuzzy dark matter. So we ran these 8 simulations, and now it's finally time to look at how the halos evolve and collapse and stabilize in the fuzzy model compared to the cold dark matter model. And a good way to observe this collapsing process is through tracing the radius of the halo over time, which we show here for all of the different runs. And so there are a lot of different lines here, but let's take, for example, the high mass, high overdensity runs. And in both the cold and fuzzy cases, we see the halo expand at the beginning before it turns around at some maximum radius, and then it begins to collapse, which I've marked here with these vertical lines. And then eventually it's going to stabilize at some equilibrium radius. Notice that the fuzzy dark matter halo collapses later and also stabilizes at a larger radius. And in another case, the fuzzy halo doesn't even finish collapsing before the present day. And in this way, it looks like the collapsing process is delayed and suppressed in the fuzzy model. And we can also see this in the final overdensity profiles of the different halos. Again, let's focus on those same 2 runs. While the cold dark matter profile keeps increasing toward the center of the halo, the fuzzy dark matter profile flattens out at a much lower central overdensity. And so again, we can see that the fuzzy dark matter halo can't collapse as much. And this is likely due again to that additional quantum pressure term, which suppresses collapse and causes there to be a minimum requirement for small scale structure formation to even occur. But what is that requirement? What is the critical overdensity needed for collapse to even happen? And if we go back to before, when we were tracing the halo evolution over time, we marked the point at which the halo collapsed. And we can calculate the overdensity of the halo at that point in time for all of the different runs. And then we can plot these critical overdensities as a function of the halo mass. And for the cold dark matter case, the critical overdensity is always around 1.686, which is expected from theory. But then you can see in the fuzzy case that the halos require, in general, higher critical overdensities, especially on the lower mass end. And this is in line with the idea that suppression from quantum pressure is going to be greater at smaller scales. But what do these critical overdensities actually tell us about small scale structure formation? What does it really mean when it comes to predicting the numbers of satellite galaxies compared to the cold dark matter case? And for this, we need to look at the halo mass function. So we'll take the ratios of the critical overdensities in the fuzzy model to the cold dark matter case, which is exactly what we've done here. And then for lack of more data points, notice that we've added another guess point at 10 to the power 11 solar masses, where we estimate that ratio to be 1. And for now, this is okay because at very large scales, we expect cold dark matter and fuzzy dark matter to behave very similarly. So we do this, and then using the different data points, we can find a fitting function for the ratio of critical overdensities with respect to different masses. And then we can put this fitting function into a semi-analytic model called Galacticus, developed by Andrew Benson. And then it'll give us a halo mass function, which I've shown here. So this shows the abundance of dark matter halos at different masses. And you can see that while the cold dark matter and the fuzzy dark matter agree at large scales, there are much fewer halos at low masses. And so we've been able to capture the suppression of small scale structure with this halo mass function. And in the future, it would be interesting to also compare this with observations of halo abundances as well. But overall, there are a lot of promising signs that quantum pressure can suppress small scale structure formation through causing late and less compact collapse in halos. And we can also see some of these effects in the resulting halo mass function. But other than that, there is still a lot to investigate. For example, can we calculate and make plots of the actual quantum pressure energy itself and look at that over time? And also, it would be good to have more data points for our halo mass function, especially at different masses. So running more simulations could be very helpful. And then finally, it would be worth it to check the capacity of our simulations in terms of the effect of higher resolutions and also checking boundary conditions. But with that, thank you for listening, and I look forward to any questions.
All right, very nice. So I actually had a question watching your presentation right back to back with Madeline's. I had a sort of new question for you that I haven't asked over the summer. It's fascinating what you guys are finding with these fuzzy dark matter halos. And one thing that I was wondering about is I don't really have a good concept of how sort of numerically challenging these are in terms of computing. But would it be possible actually to look into what one of these sort of fuzzy dark matter simulations would show for substructure within a halo? So you might imagine that these sort of more extended halos would be easier to disrupt even just gravitationally in a larger halo. And I'm curious if that is something that's even really feasible at this point, or if you know. I know this is like very different than anything you've talked about this summer, so no worries if you don't have an answer.
Yeah, that's a really interesting question. I wonder if we can capture the existence of those like smaller substructure halos, like subhalos, using another version of a halo mass function. So this would also be interesting. But yeah, that's a really good point, and it would be interesting to look into.
Awesome, thank you. It looks like Josh has a question. Go ahead, Josh.
Yeah, I may have missed this, but what is the fuzzy dark matter particle mass that you were using in your simulations? And do you have any predictions about how the suppression of low mass halos would depend on that?
Yeah, thank you for your question. So in our simulations, we were using a particle mass of 10 to the negative 22 electron volts. And that is the same particle mass that we use to make our halo mass function in this plot. But then something that we can do further is to also make a similar halo mass functions using different particle masses. So here I've shown it for like half of that, and then also 10 to the negative 21 electron volts, and making a similar halo mass function. And I guess we can explore like what would be the true mass of the fuzzy dark matter halo particle by also plotting observations and seeing which particle mass yields appropriate suppression in order to match observations. And I guess to answer your question, my initial observations from this plot is that the lower the dark matter particle mass, the higher the suppression is. And this would make, oh, sorry, the higher the particle mass, the higher the suppression. Yeah. I hope that answers your question.
All right, very nice. Thank you so much.